Okay, so what we'll look at today is the last official developed lab. The final project we'll talk about next week. My advice is it'd be highly beneficial to be online next week, and then we can really talk about what I'm expecting from you with the final design, the final project. So in this lab, what we're going to do is we're going to look at the issue of service line material identification. And with that, you will monitor or determine soil and water pH, and with that also determine soil type. So just looking back kind of a few years ago, Flint was on everybody's mind. It may still be in many cases. But what we observed in Flint was a significant increase in the lead concentrations as a result of the change from purchasing water from Detroit Water and Sewer Department that had been treated import urine, it was lake urine water, piped to Flint, and then distributed. In April of 2014, they switched to treating Flint River water in Flint and distributing that. And that resulted, as many of you, I'm sure, are aware, significant health issues, water quality issues in the city of Flint that also led to, in some cases, elevated blood lead levels among children. Well, this is just the results from the later part of the monitoring efforts, looking at the lead levels in Flint. Now, lead is measured in homes that have are reported to have lead service lines. And in Flint, at this period of time, there would have been about 66 samples taken over a 6-month period, and then they determined the 90th percentile level. And you can see that the 90th percentile level was dropping significantly. The action level, as shown here, is the level at which a decision is made as far as optimal corrosion control. So if the level is above 15 parts per billion, then the water system is determined to not have achieved optimal corrosion control, and they have to take measures in order to optimize corrosion control. Well, as a result of what was happening in Flint, there was a significant number of utilities that were then required to also monitor lead levels. And this is from 2017 and 2019, but it's indicative of what has happened across really much of what we refer to as the Rust Belt, much of these older cities where lead service lines were used for distributing water. And you can see the article on the left talks about 71 Michigan water systems have higher lead levels than Flint. The one on the right in 2019 says that 13 Michigan water systems flunked the federal tests, the 15 parts per billion lead level, in the action level for drinking water systems. Now, and this is just another image. Again, this is from back in about 2018. And again, looking at lead levels in Michigan. And what you see is that a significant number of cities, both in Flint and outside of Flint, have action levels or have 90th percentile levels that are alarmingly high, which this means that there's the potential for people to be exposed to lead in their drinking water. And you just finished an assignment looking at how New Zealand has dealt with the issue of lead in drinking water. Now, in New Zealand, they've actually never used lead service lines. They don't have any source of lead. In New Zealand, it's in Oceania. It's expensive to ship. So my guess is for that reason, they have never used lead service lines. This is just another plot. This is from Benton Harbor. And here's the action level and the 90th percentile. Here in Benton Harbor, it was 21 parts per million, so it is in excess of that action level. So they had not achieved optimal corrosion control at this point in time. The bottled water standard is actually 5 parts per billion. Bottled water is not regulated by EPA. It's actually regulated by the Food and Drug Administration. But they have a different standard from drinking water. Now, as a result of the concerns about lead in drinking water, the state of Michigan in 2018 promulgated its own lead and copper rule. It is more stringent than the federal lead and copper rule and requires for number one, a inventory of all service lines. In the past, they needed an inventory of the lead service lines. Now, the state of Michigan says that all utilities must submit to Eagle by January 1st of this past year an initial report of how they will determine the lead service lines in the communities which they serve. And then by January 1, 2025, they are required to submit a comprehensive updated inventory, and they must maintain this inventory and every 5 years submit a updated inventory. So this is a very significant difference. They also must notify residents served by a lead service line within 30 days of determining the service line material. So for instance, here, you can see this is before. Notice in the image here, this is some sort of a plastic pipe. They don't know what is on the public side, so this is where the curb stop would be. And you can see after, once they commit, do the inventory, then they have to identify both what's on the private side and what material is on the public side. And you can see, so in here, we've got lead and lead. So the minute they identify that, then, well, within 30 days of that point, they have to notify the homeowner that they in fact do have a lead service line. And same thing here. So that's quite more, it's quite and much more stringent than the federal regulation. Another requirement is that the utilities will be required to replace the lead service line, and they must do a complete replacement. So for instance, and let's just look back here, what you see here is this is copper and lead and copper and lead. These are two different dissimilar metals. When you have dissimilar metals, you have greater potential for corrosion. When they replace this, it has to be replaced with, for instance, copper in both sides. So they must remove all of the lead. Here, it's lead and lead. When they do the replacement, they can't do what we call a partial replacement. So for instance, they couldn't just replace the lead on the public side. They must replace the lead service line on both the public and the private side. So that was a significant change. They also must replace any lead goosenecks. Basically, the gooseneck is that portion of the pipe that comes off of the main, and lead was often used for this because it's extremely malleable, and you've got vibrations from the road, so you want something that actually is more giving than, for instance, copper. So lead was often used as the gooseneck. So that has to be replaced. So no partial replacements, full, complete lead service line replacements. So even the gooseneck is now considered part of the service line and must be replaced. That was not in the original federal lead and copper rule. It also changed the way or the regulatory limit. There was a big debate with this, whether it would be, what level should it be used. It was decreased from 15 down to 12. The health communities wanted it lower, but as often happens with legislation, there's negotiations and compromise, so it was set at 12. The other difference is how the testing is done. So in the past, it was a 1 liter first straw sample. So the idea was you took the sample first thing in the morning of the water that had been stagnating in the pipes. And that was the sample. So it's full flow and 1 liter sample. Now you do a sequential sampling. So you take that 1 liter, you analyze that 1 liter. This gives you an indication of the lead level that's really coming from household premise plumbing, including the fixtures, because brass fittings contain lead, so that lead can leach from the brass fittings. And then, so you take 5 sequential samples, you analyze the first one and the last one, and the 5th is an attempt to try and get a better representative sample of the water that's actually in the service line. Be interesting for you to think about this in terms of the analysis that you just did with looking at premise plumbing. How representative do you think this 5th liter sample is of what is actually in the service line? Another requirement is public involvement. In the past, that was not required. Now water boards need to be set up. A public needs to be informed. The public needs to be given the opportunity to respond to all of this data gathering, all of this information, and to any changes that are made in the system. Any questions about kind of background? So I've shown this slide before, but again, I really want to reiterate what we're looking at in terms of these distribution systems. And we've talked about the distribution as a whole, what we're focused on is right here, is what is referred to as the service line, typically what is public. This is your curb stop. That's where the shutoff is. As part of the lab, or the assignment 3, you should have actually gone out and looked for that brass plate where the shutoff is. And then this is the private side. And the gooseneck would be right in here. This is another little cartoon trying to show where lead can originate in a home. And that includes copper pipe with lead solder. Now the solder that was used before 1986 contained much higher levels of lead than is used now. So that has a potential source of lead. We've talked about the lead service line, the goosenecks. In addition to that, fixtures may contain lead. In 2014, the federal government passed a regulation changing the requirements for what we call lead-free fixtures. So previously, what was considered a lead-free fixture could contain up to 8% lead. Now it was redefined and reset at 0.25%, and it's the the wetted surfaces in the faucet itself cannot contain more than 0.25% of lead. Lead is in there because in the manufacturing, it makes the manufacturing process easier. Galvanized pipes can also be a source of lead. So for instance, if you have lead upstream here and the rust particles or rust inside a galvanized pipe can absorb the lead particles, and essentially that galvanized material becomes a continual source of lead as that lead either flakes off or dissolves into the water. So in terms of service line materials, they can be copper. And as many of you learned, there are multiple types of copper. So there's K, L, M, and then there's DWV. K is the thickest, M is the thinnest. L and M are what are most commonly used for interior plumbing. And then in older homes, you may find DWV, but these typically were not used for a distribution system. This picture here shows a copper line, and what you're seeing here is actually most likely lead solder. So galvanized is a iron pipe coated with zinc. And you can see a new pipe on the left and a severely corroded pipe on the right. And you can see it's really in here when I was talking about the rust particles that can absorb lead. And then we can have lead pipe, and here's what a lead pipe looks like. And this is likely a joint where the lead pipes were joined. We also are now using cross-linked polyethylene or PEX pipe. You'll often see that. And it comes in either red, blue, or white. And red is used for hot water, blue for cold water, and the white can be used for either hot or cold water. And then we have polyethylene PE. And that's typically looks like this. So we have multiple service line materials. And the challenge is to identify those materials. What you will often find is that the consistency of the pipe material throughout the service line will depend on the city policy. So for instance, if you go to Grand Rapids, you'll see more of the same service line material on both the public and private side. In Flint, when they did the identification of lead service lines, they found that 80% of the lead was just on the public side, not on the private side. You'll also find mixed metals. This is actually a photo from inside my brother's home, and it's at the meter. And you can kind of see this kind of goofy water comes in here, goes up this way. You see multiple different metals. You see brass fittings. This is actually a pressure relief valve right here. So how do we detect the service line material? It's required now to determine, do this inventory of service line materials throughout the entire state of Michigan. We do visual inspection. So we can go back and we can look at something like this. But does it tell us what we need to know? Well, for instance, at my parents' home where I grew up, they always thought that they had a galvanized service line. What the pipe that came through the wall of the house was built in about 1920 or so, but the pipe that came through was galvanized. So they assumed that they had a galvanized service line. And that's what they thought they had until they had a service line leak, and they had to have the plumbing company and the utility come out and investigate, and they learned that they had a lead service line. What the pipe coming through the wall of the house was galvanized. Everything else beyond that was lead. So visual inspection isn't necessarily going to tell you what that lead service line or what that service line is made of. So then we can do hydrovacing, and basically what you do there is you use kind of like a pressure washer to remove the soil, and you can visually inspect, but again, you're really just looking at that particular area, typically around the curb stop. So if there is a change, and when my parents had the leak, they decided that they were just going to replace a portion of the pipe that was leaking. So what they did was a partial replacement. So they had copper, but everything else was lead. So again, now they've got, if they did a hydrovacing, it actually would have shown that there was lead, but they actually had a portion that was copper. You can excavate, but that actually is expensive. It's extremely disruptive because you're excavating the entire front lawn, basically. We can look at historical documents. Fortunately, those are not very accurate. Under the federal lead and copper rule, cities and utilities were required to maintain those. They were supposed to computerize those. For instance, in Flint, there was something like 60,000 index cards in a filing cabinet, none of which had been maintained. So the question is, can we develop novel methods to allow us to detect leads or detect service line material without having to disrupt the soil, without having any invasive type measures taken? So one method is electrical resistance. And what I've done is design this as if you were part of a design team. I based this on a project that was done in the spring with several CE 495 students, and several ECE 480 capstone students. So what they were attempting to do, and unfortunately because of COVID didn't get quite as far as we had hoped, but what they were trying to do was to develop a non-invasive testing method based on the different electrical resistance of materials that would allow them or allow a utility to go in, connect at the curb stop, perhaps connect at the meter, and then based on that information could determine resistance and then determine the service line material. So one of the questions that was asked was, how does the variability in soil pH and soil conductivity affect the resistivity of this pipe material? And that's where we were hoping to really get at, looking also at the effect of corrosion and soil water moisture content, also on resistance. So your job here is to help contribute to this. So what you'll be looking at is, how does pH and conductivity vary based on soil type? Given what we can accomplish at home, this is pretty much what we can accomplish at home. So what you will do is you will need to obtain 4 soil samples. Each student will obtain 4 soil samples. You'll need distilled or deionized water. If you are located in the East Lansing area, I can get you distilled deionized water from the lab. We can figure out a time to meet, and we'll make sure you get that. If you're not, you should be able to purchase distilled water from a grocery store. If you can't, let me know and we'll figure out how to kind of juggle things. You'll need some clean glassware. You'll need a 1/4 cup measuring cup, tablespoon measuring spoon, and some plastic disposable spoons for mixing. You'll need 4 mason or large jars. You can use a spaghetti sauce jar. You could probably use a 1-liter Gatorade bottle. You just need something that you can put the soil in, that you're going to let it settle, and then you will measure and we'll explain what you'll do for the soil type. Okay. So your 4 soil samples, you'll need to record the location where you obtain these. You might want to dig a hole about 1 and 2 foot deep. If you need, again, if you need any equipment, just let me know and we'll figure out how to get that. It'd be nice if you have some soil that is distinct differences in color and texture, and that's why I said if you dig down, you'll see some differences on the soil horizons. So you'll see some differences with depth. You can sample along the riverbank, a wetland, your backyard. Just be safe when you obtain the samples. So what you're going to do is you're going to prepare a slurry of the soil samples for your conductivity and pH analysis. So the ratio of the soil to water should be 1:1, and that's actually weight. So for instance, 60 grams of soil is about 3 tablespoons of soil. Mix that with 60 grams, so about 1/4 cup of deionized or distilled water, and this is why you want the deionized distilled water. Mix that, and then what you'll do is you'll decant a small amount of the water into the pH cuvette, follow the instructions and measure pH. You'll also measure conductivity by just submerging the tip of the conductivity meter, and you'll record pH and conductivity. And then for each soil sample, measure pH and conductivity 3 times so that you can determine the standard deviation and confidence intervals. Now for soil type, soils are classified either sand, silt, or clay, and this here gives you an idea of the relative sizes of the material and colors. So sand, coarse sand is the largest, followed by medium sand, fine sand, silt, and clay are the smallest of the particles. Sand is, sand, it's kind of rough, gritty, grainy. Silt tends to be slippery and smooth, and clay tends to be sticky and moist. It's the clay that you played with as a kid and could make kind of mud balls out of. So what you will do is you'll spread the soil on a surface. You can use newspaper, paper towels, cardboard, a plastic grocery bag, anything you can use to just dry that soil material. You'll remove any rocks, trash, roots, etc. And then you'll crush any lumps or clods of material, kind of pulverize that. You can use a hammer and a mallet. You can use basically anything. Probably could use your foot to kind of pulverize it, your shoe. But basically what you want to do is pulverize the soil. You then will fill a tall, slender jar. So canning jar, like mason jar, clean spaghetti sauce jar, anything that is relatively tall, slender jar. So you'll add water until the jar is 3/4 full. Then you'll add a teaspoon of non-foaming dishwasher detergent. Again, if you need anything, just let me know. Especially if you're in the area, I can help you out a little bit more. If you're not, we'll figure out something. You're going to put the lid on. You're going to shake it hard for about 10-15 minutes. And this breaks apart the soil aggregate, separates the soil into its individual mineral particles. And that's what you need to do in order to do the soil testing. And then you'll set the jar in a location where you can leave it undisturbed, away from the sunlight, for 2 to 3 days. So when you're thinking about your experiments and turning it in, make sure you're thinking about the fact that you do have to leave the soils for about 2 to 3 days. So after a minute, you're going to mark on the jar the depth of the sand. So you can see here, got your sand layers here, so mark the depth. After 2 hours, you'll mark the silt layer. So make sure you can mark that because you're going to need that information later. And then when the water clears, you can mark the depth of the clay layer. And that typically takes about 1 to 3 days. It can take longer, which we don't have longer. So that's why I'm saying leave it for where you can leave it for 2 to 3 days. And then what you will do is you measure the thickness of the sand, where you've recorded the sand, thickness of the silt deposit, and thickness of the clay, and the thickness of the total deposit. And then you'll calculate the percentage of sand, silt, and clay. And then what you will do is you will use this soil texture triangle to determine the soil texture class. So I'll illustrate in the next how to use that. So for instance, and I gave you the link, and the link allows you to put this information in, and it actually will automatically put the red dot on the image. But I also wanted to show you how it obtains it. So in this case, for instance, we have a soil with 50% sand, 20% clay, and 30% silt. So we have 50% sand, we have 20% clay, and 30% silt. And where those 3 lines intersect that tells you what type of soil this is. So this would be a loam soil. Just looking at another example here. In this case, we have 10% sand. We have 70% clay. My mouse is misbehaving. 70% clay and 20% silt. And where those lines intersect is the soil type. So this is a clay soil. And the third type here, you have 70% sand. You have 10% clay and 20% silt, and this is a sandy loam. So depending on the percentage of these three types of soil materials, you can then determine your soil type. Like I said, it's really easy. You can use the triangle here, or the notes have the soil texture triangle link. It's a USDA site, and you can simply go in and plug in the values, and it will plot it for you. And then you'll record the soil type. So for the analysis, on a map, you will show your sampling locations. You will report all of the results in tabular form. If you have similar types of soils, think about how it would be best to report that information for the audience, which it would be you're providing the information in this case to a ECE 480 and CE 495 group that is working on this project. If you have similar soil types, then use ANOVA to determine if the differences in the concentrations measured are statistically significant at a 95% confidence level. You can also plot the data with the confidence intervals, because if you remember, that provides us with some different information versus what we get from the ANOVA. So think about how variable are the pH and conductivity of the soil types that you have looked at. Do you think these differences would affect the measurement of resistance of a pipe material? And are there methods that you could use to improve the experimental technique? So think about this, okay, we're no longer in the pandemic. There's a group of CE 495 and ECE 480 students that are continuing this project. What would you recommend that they do differently than what you could have done being at home and having done the experiment the way that we did? Also think about reporting. So remember, you have limits on your reporting. If the pH is below the limit of your test, then you report less than some value. If it's greater than, you report greater than whatever that value. So your report is to take the form of a memo to the students and faculty of the ECE department, doing ECE 480. You can include the CE 495 students if you'd like in that. And you're going to present your objective, a brief description of your methods, the map of your sampling locations, your finding, discussion, and recommendations. You're providing your expertise, especially to the ECE 480 students, regarding measuring soil pH and conductivity and the variability and the influence of soil type on these parameters. Supplemental section is the same as always. And any questions?